In looking at example 5.2.1, I wanted to point out a few things about a probability distribution table, like what's shown here. The problem sets up the situation. A child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X equal the number of times per week a newborn baby's crying wakes its mother after midnight. For this example, X equals 0, 1, 2, 3, 4, or 5. P of X is the probability that our random variable X takes on a value of lowercase x. Don't let the capital and the lowercase x's confuse you. It can be. The capital X is what we call our random variable. So capital X is our random variable that can take on various numerical values. The lowercase x represents the values that the random variable can assume, the values the random variable could be. Some textbooks actually just call that column capital X instead of lowercase x, so you may see that in other textbooks as well. This table here that gives X and then corresponding values of probability is what we refer to as our discrete probability distribution. Sometimes this is a probability distribution function, a PDF for short. And the idea here is it's discrete because we have a countable number of values for X. We can count them. 0, 1, 2, 3, 4, 5. There are 6 values for X. That's why we get it as a discrete probability distribution. And then the column on the right gives us the probabilities. The probability that our random variable takes on one of those values of X. Now, this information in a probability distribution will either be given to you as a table like it is here, or it could be described in the text above. Or it could be described by a function itself, like in algebra, and you'll see some of those a little bit later. But there are 2 properties that a discrete probability distribution must have, and those 2 properties are listed below. Each probability is between 0 and 1, inclusive meaning we could have a probability of 0, and we could have a probability of 1, but every probability listed over here on the right has to be a number between 0 and 1. And then the second property is that the sum of the probabilities must equal 1. And they've written them out here for us: 2 50ths plus 11 50ths plus 23 50ths plus 9 50ths plus 4 50ths plus 1 50th. If we add up all those numerators, 2, 11, 23, 9, 4, and 1, we should get 50. 50 divided by 50 gives us 1. A reminder that this is something very similar that we've already talked about in Chapter 4 with sample spaces. Every probability is between 0 and 1. That's a property of all probabilities. And then Part B, the sum of the probabilities is 1. This is true for a sample space. You could almost think about this discrete probability distribution as being over a sample space, because it essentially is. We're actually over a population, not just a sample. And in that sense, the sample space that we talk about in Chapter 4 with probabilities is not the same as taking a sample from a population. Those are different, in case that's not very clear. And there you have it, our discrete probability distribution function. We'll be using these 2 properties as we go throughout the chapter. You're also going to see these 2 properties come back up in Chapter 6 when we talk about continuous probability distributions. In the examples coming up, you'll see how we would interact with this, how we could use it to answer questions, and how we can fill in gaps if we have them.